In the last years, we focused primarily on the genomics evaluation. We delayed the development of carbon trace evaluation. Now I'm going to present to you our new multiple parity carbon trace evaluation model plus some genomic information. The previous evaluation model for carbon trace was a single trait repeatability model with correlated direct and maternal effects. The main drawbacks of the old model are the first, there was no separate heifer breeding values available, although we know that heifers have more carbon difficulty than cows. And also we used old data which were not very well harmonized across regions in Germany. Because of no participation in the interval carbon trace evaluation, we had our genomic reference population for the carbon trace was much smaller than for other traits. Our new model for carbon trace differentiate heifer calving from cows, like in Canada, Nordic country, and the Netherlands. And we use the first three calvings and treat them as genetically correlated traits in the same way as we used in the testing model and female fertility model. We considered calving is a stillbirth, and we use only the most recently data well harmonized since 2000. So the calving has 4 classes, and stillbirth is defined as a calf being live or dead within 48 hours. So the model is a 2-trait, 3-parity linear animal model with correlated direct and maternal effects. In a fixed fat consists of herd year effect on a herd level. We have region, year, calving season, and calf sex on the regional level. And on the population level, we have year, month, calving age, calf sex. So in total, there are 12 EBVs per animal, 2 traits, 3 parities, and 2 effects. And prior to the estimation of breeding value, we performed the Snell transformation of score within parity, region, year, season, and calf sex classes. For the April 2012 national evaluation using the new model, we had 21 million calving records from more than 500,000 herd year classes. So the number of animals providing data, so calves and cows, reached 27 million. And each year we add 2.5 million new animals into the system. And there were 33 million animals in the pedigree connected to the data. And the equation system was about 400 million. And for the April May evaluation, we sent more than 21,000 AI booths to interval. This graph shows you the phenotypic trend in the calving and stillbirth. And you can see the black line, that's the stillbirth, around 7%. And we have 4 classes of calving ease. And on the population level, we have about 70% easy calving. And after the second harmonization in 2005, the frequency of each classes are more homogeneous across years. For estimating the genetic parameters, we used the linear sire maternal ground sire model in order to consider a lot of data. Gestation length was initially considered together with timing and stillbirth, but based on our genetic parameter estimates, we decided to remove this trait from calving trait evaluation. And the data for the parameter estimation originated from April 2010. We selected large herd year parity classes and also large progeny, large family size for bulls. So in the final data set, we had about 2 million carving records, more than 3,000 bulls. And because of the computing requirement, we divided the whole parameter estimation into sub-analysis, but we require that each sub-analysis must have 3 parities to avoid any selection bias. The covariance estimates were averaged across sub-analysis. And finally, the covariance estimates of the sire maternal grandsire model were converted to the animal model with direct and maternal effects. So this table gives you the genetic parameters of the new calving trace model. We have here direct effects of calving yeast, stillbirth, as maternal effects. So on the diagonal, we have the heritabilities. You can see they are very low. For the first parity, for example, the highest heritability is maternal stillbirth, 5.4%. Lowest was for the direct stillbirth, 2.7%. And the correlation between the parities was about 0.9 for direct calving yeast, 0.8 for direct stillbirth. We have lower correlations between parities for maternal effects. So clearly, we can see here the genetic correlation between parities are less than 1, which justified multiple parity calving model. And one important parameter for the direct maternal effects is the correlation between direct and maternal effects. They are all close to 0, mostly to negative, except the third parity stillbirth. We got a slight positive correlation. The mixed model equation was solved with special monitoring the correlation between the direct and maternal effects estimates. And when we applied multiple trait EDC and reliability method to calculate EDC and reliabilities, when we calculate the data contribution, we accounted for the fact that calf and cow share the same phenotypic records. The official breeding values are defined as the first parity EBV. Basically, we put 100% weight on the first parity, and the minimum reliability is 35%. And we publish also the direct calving index and the maternal calving index by equally weighting the calving yeast and stillbirth. And only the maternal calving index is included, total measured index LZG, with currently 3% weight. So this graph shows you the genetic trend in the I should have this one. The maternal effect, the trend in maternal effect in hosting bulls. Here the large value means biologically better or favorable. And you can see relatively flat trend here, but in the last years, we had some positive, favorable trend in both maternal effects of calving yeast and stillbirth. For the direct effect of calving yeast and stillbirth, the trends are rather flat. Then we validated our the new multiple parity calving trace model using the interval validation method 3 by truncating the last 4 years data. Then the EBV from this truncated data set were compared to the complete data evaluation. And then according to the test, the maximum trend estimate must not exceed 2% genetic standard deviation. Here you can see they are within the lower than the allowed trend estimates. And in the January test run, interval estimated genetic correlations between Germany and other countries using our new calving trace model. These are the average country correlations between Germany and all other countries in the direct calving yeast evaluation. We have for the Carmian traits block, we have relatively good correlations, particularly with the major countries. And for the direct stillbirth, this is we got lower correlations. That's also observed for other countries. And we also studied genetic trend of maize evaluation by country of origin. So for the genomic evaluation, we use the maize breeding values. We deregressed the maize breeding values for all the hostings. So we took all the hosting bulls in the maize evaluation and to obtain the deregressed EBV for all the 4 Carmian traits. Then we combined this deregressed EBV with urogenomics genotypes to set up bull reference population. You can see here for direct Carmians, we had more than 22,000 bulls. Direct stillbirths has lowest, smallest reference population. Then we estimate SNP effects for 5 scenarios of residual polygenic variance from 0%, 1, 5, 10, 20%. For the routine genomic evaluation, in April, we considered all the 54,000 genotyped animals. And our routine genomic evaluation model is a single trait BLAP SNP model with residual polygenic effect, and also the residual polygenic variance is trait specific. Now this graph shows you the, give you some SNP effect plots, that's Manhattan plot. When we used the national breeding value to estimate SNP effects, and the reference, we had less than 10,000 reference bulls. And you can see these are the SNP effects, that typical for BLAP SNP model. But you can see here on the chromosome 18, we have a major gene for direct effect Carmians as well as for the direct effect of stillbirth. But this major gene has no impact on the maternal effects. When we switched to maize breeding values, the reference bulls increased to close to 23,000. And you can see here the SNP effects are more variable, the variance increased, and also the highest SNP, largest SNP now is 6.5 standard deviation from the mean. But here, the same SNP was something 3.6 standard deviation from the mean. We took the interbull January test run, the maize EBV for the genomic validation, because we did not have any historical data for our new model. So we decided, we had to separate the current reference population into the smaller reference population and the validation population by using the birth year of bull and direct effect and maternal effect. They have little bit different reference and validation populations. So the validation bulls are the German national bulls, and also for these smaller reference populations, we estimate SNP effects for all the 5 scenarios of residual polygenic variance. Based on the interbull GEBV test, we determined the optimal residual polygenic variance is 20%, but for the maternal stillbirth, 10% is enough. And genomic reliability ranged between 0.49 to 0.59. And for maternal stillbirth and direct Carmians, we got highest reliability because of highest heritability or high country correlations and the most reference bulls. However, for the direct stillbirth, the genomic reliability was lowest. That's because of lowest heritability, lowest country correlations, and lowest number of countries or bulls in the maize evaluation and consequently in the reference population. Certainly, it does not help that 4 out of 12 countries sending Cavendish direct effect into the Stilbert's direct effect maze evaluation as a predictor trait. When we compared genomic reliabilities to the previous model, we found significant increase, about 11%. That's mainly due to more accurate conventional evaluation model and more harmonized data. And most importantly, that's because of we have much larger reference population using the maze EBV instead of national breeding values. Now, I would like to conclude my presentation. So we have developed a multiple parity model for Cavendish evaluation. The correlation between the parities clearly lower than 1, which justified the multiple parity model. And we passed the new model passed the genetic trait validation test. And we obtained also reasonably high genetic correlations with major countries. Using the trait-specific residual polygenic variants, the new trait evaluation model passed GEBV tests based on the B1 value, and we started the new model in the routine evaluation and genomic evaluation in April 2012. The next step will be a single-step SNP model for joint genomic and conventional evaluation. So I would like to thank the Protege group and Pete for useful discussions and Eurogenomics for providing genotypes. So before I end my presentation, I would like to invite you to Berlin for the 2014 ICAR and Innsbruck conference. Thank you.